Hi, this is Mike Tochik. I'd like to talk about aspects of station design today that involved forgotten combinations of overvoltage protection along with cathodic protection isolation. We want to have overvoltage protection for safety and also cathodic protection for effective corrosion prevention. Here are the topics we're going to talk about today. We need to talk about how you are exposed to voltage within a station and what those risks are. We'll talk about what are the actual overvoltage protection requirements to afford protection for workers. That gets us into such issues as bonding, isolation, and grounding so that we do those effectively and in the right situations. We'll do that by looking at example station construction. So we're going to build a station from the ground up and look at how we protect or cathodically protect at the right locations within the facility. And there's a couple last factors for us to talk about also, including practical designs and where you draw the line on station design for cathodic protection and tie-ins to such issues as hazardous locations. So here are the situations typically found in a pipeline facility. What's often known to the user is the fact that their CP has been affected. They know that via cathodic protection readings, and that says by default that they somehow are bonded to other structures when they have low readings. So they generally know when cathodic protection is unacceptable, and they infer that they're bonded or shorted to other structures. Not that we want that to occur. What might be less obvious is when the opposite occurs. When CP is fine, but what they might not be focusing on is that those structures remain unreferenced to ground, or they are unreferenced to other nearby structures, and then those points can support voltage. Finally, another less obvious issue would be if any of this is in a classified hazardous area, and then certain products and methods and practices must be employed. When I use the term referenced, what I mean is that the structures are bonded or a structure is grounded, and therefore it can't support a voltage difference between, say, pipeline and ground, or one pipe and another pipe, or between there and a fence. When something is unreferenced, what I mean is that it's not bonded, there is an open circuit, and if that's true, then if voltage is present, then it can support that voltage difference. The goal with overvoltage protection is to limit the voltage between 2 points of concern. So that could be at many points within a facility or out in a pipeline, such as across an insulated joint, where one side of the insulated joint, that steel, could be at a different potential than the other side. Or from pipelines to grounding systems or pipeline to earth. It could even be between one grounding system in a facility and another grounding system, or it might be between your grounding system and, say, a fence, which is tied to someone else's grounding system. There even can be voltage differences across a single existing grounding system with you standing over it, and that's a special case where there's a high gradient, voltage gradient in the soil due to AC faults or lightning. And then we have to think about whether any adjacent structures can be contacted simultaneously, whether that's a fence or a building relative to the pipe or a grounding system. And what are the sources of this voltage? Well, that would come from an AC fault or lightning strike, or possibly steady-state AC induction out on the pipeline being transmitted or transferred into the facility. Ironically, even as I'm recording this conversation, there's a lightning storm nearby, and you might be able to hear that in the background. So let's look at unreferenced structures. If a pipeline has no protection across an insulated joint or no reference or bond to a grounding system in a facility, that remains unreferenced to each other. So therefore it can support voltage. In this graphic, across an insulated joint or from each pipe segment to ground, there's no protection. We might have effective cathodic protection this way, but we have not addressed overvoltage protection. So what we need to do is provide effective DC isolation so that you can have effective cathodic protection, and we don't want to pick up stray DC or have interference situations, but we also need personnel safety provided via overvoltage protection. And station design has to include both concepts. But generally, the focus of the energy industry will be cathodic protection and compliance at the expense of overvoltage protection, which is just not understood or is only incompletely addressed in a station design. Let's go ahead and build a facility and talk about all of the elements that are in that facility and their relation to overvoltage protection or cathodic protection. We'll deal with both as we go on. So what we have here is a pipeline entering a facility and leaving again cross-country. Let's look at some of the features of this station, and that includes, starting from the lower left, a cross-country pipeline, and let's make that be an impressed current cathodic protection system with a rectifier, coming up through an insulated joint and a motor-operated valve, back below ground again for a short run, and let's make that be a galvanically protected system, through another insulated joint, then into a building where, let's say, we meter gas and have other electronics or equipment inside the building, out the other side through a gas-operated valve with insulated joints around it, and finally out to a different impressed current cathodic protection system. We'll call that CP2. The points in this facility that, if no action were taken, can support a voltage would be the insulated joints. We see that we see 3 insulated joints in this picture, actually a 4th in the upper right also, and those can support voltage if they're not protected. Also in the building, let's assume that we have to address equipment for piping that passes through the building that might remain unreferenced to the building or grounding system. The way that we'll address overvoltage protection of the insulated joints will be to install a decoupler, an appropriately rated decoupler, across the insulated joint. Note that it's not connected from pipe to ground or pipe to the station facility, but rather directly across the insulation system itself. That's the best form of overvoltage protection to address inductance issues and lightning-related matters. We do have a couple more points that we haven't looked at yet. The first one would be the equipment in the building. So that equipment can rise in voltage if it's not referenced to the building, and there has to be some appropriate means of addressing that. And then also in the upper right, we see another insulated joint that doesn't have a decoupler across it, but it is in parallel with an existing decoupler. And the question is, what action is needed there? Let's take the case of the building first. Because between these insulated joints there is no cathodic protection in the building segment, we can just solidly ground all equipment to the building and its grounding system or back to an electrical supply panel, and there's no effect on cathodic protection. And we've also provided overvoltage protection. Now let's look at the insulated joint that's in the upper right. It is possible that that insulated joint could receive overvoltage protection from the parallel decoupler up above. In some cases it can, in other cases it can't, and that relates to how long of a conduction path we have and what its inductance is, an electrical property called inductance. And this effect of inductance interacts with fast-rising waveforms, such as from lightning, where you can still end up with a high voltage across the point. And we wouldn't want to leave a point unprotected and then still have it flash over due to a fast-rising waveform like lightning. It won't happen with AC faults, but it could with lightning. The example of where you'd have such a situation is like in this picture here, where the main pipeline with an insulated joint has in parallel with it a bypass or run with another insulator. One would have to consider the incidence of lightning for your proposed installation and whether the inductance of this other bypass, this other path, is excessive and therefore might need its own decoupler across that insulated joint. Here's an example of a good installation where the protective product, the gray rectangular box in the center, is connected very tightly across the insulated joint. It's a little bit difficult to see, but there's formed copper bus bars that mount the decoupler terminals across the flange faces to provide close, tight protection. What this is doing is providing a low inductance path to give the best overvoltage protection due to lightning as well as AC fault conditions. Now let's look at how we actually provide protection if there was a fault out in the pipeline and how the station interacts with that. If there's a fault out in the lower left portion of our drawing here, where the pipeline, say, is in a parallel right-of-way with a power line, and a fault affects that pipeline, if fault current flows, its path to the grounding system, separate from any other mitigation system which might exist, is via the series connection of two decouplers across the two insulated joints, not just one of them. So in order for that voltage to be addressed relative to station ground, it's separated by the series connection of two insulators and therefore two decouplers. We wouldn't want to leave one of these joints unprotected, or we could end up failing that insulated joint, or in the case of our example station right here, CP section number 2 just had a galvanic anode on there, and we might end up failing the lead of that anode in the process of passing fault current. Now let's look at some of the various things that can short out pipelines for their CP to the grounding system. The first area we'll look at will be measurement tubing that's measuring pressure, or transducer shields that are the metal wrap around signal cables that run out to transducers, and those connect between the pipeline, direct metallic contact with the pipeline, and let's say this measurement building with its equipment. So if these were all solid and continuous, then CP could be bonded to the grounding system or maybe other structures inadvertently. The way we would normally address something like this is to install an insulated swedge lock fitting in a tube, such as on the lower right, or to create an open point in a transducer shield such that CP is now not continuous with ground. And then a decoupler is placed across that open point or across that insulated fitting. So here we've depicted a decoupler across each of those. But we're going to look more carefully at each of these two connections. Do these both actually need isolation for cathodic protection and therefore a decoupler? Well, before we address that, let's even say that we could take the two decouplers and we could make that become just one if it were located at the common point, which is where these lines come to the measurement building. Therefore, both of these tubes or shields would bond to a common decoupler terminal before the other decoupler terminal ties to the built-in grounding system. Is this going to work? Is that an acceptable approach? Well, the way to think about whether this is an acceptable approach is, do both of these connections from the pipeline come from a common CP system? Is it the same CP system? Because we're going to bond them together at a common decoupler terminal. Can we do that? Well, in this particular case, if we did this, we'd end up shorting the upper CP system to the bonded grounded station. We don't really need to do that. It would be, in fact, undesirable. Only this upper line actually has cathodic protection that could be brought to the measurement building. The lower or left-hand signal cable or tube actually is connected to a non-cathodically protected section of piping. So there's no reason to have to decouple that or create an isolation point. It can remain solidly grounded. There's no effect on CP. Only the upper one, or right-hand one, needs to be addressed with a single device. So just graphically, I've shown this as the decoupler further away from the building, just so that you can see that it's only in the right-hand line. Here's a pictorial of an insulated joint set where the measurement tubing in a series of 5 parallel lines all have been decoupled with a single decoupler. That's the black cylindrical looking object to the right, and they've all been jumpered across with cables so that one device protects this combination of 5 insulated joints and does so successfully. Now let's switch gears to another bond that can also short out cathodic protection and yet is a required connection, and that is AC equipment grounding conductors. These are the green wire or grounding conductor that go along with power conductors out to an electrical load. So in the case of a motor-operated valve on the lower left, that has a grounding conductor that goes along with the phase and neutral in order to provide safety. Or in the center in the building, there could be electrical equipment in that building that must require power and therefore have a ground. The ground is there for protection for personnel. It allows a fault to flow on the ground for if it's solid and continuous and able to handle fault current, it allows the breaker to operate. However, as installed on a cathodically protected pipeline, these grounds also cause a short for CP. Before we completely solve this problem, let's introduce a couple elements that are also in the station. There are also copper grounding grids or rods, there's grounding rings around buildings, and there might be gradient control mats out along the piping for personnel step and touch voltage protection that are also in this facility. Not only that, all of those are bonded to each other. So grounding rings tie to buildings and ground mats, and those may also tie into the gradient control mats. So basically, everything in this station ends up being bonded together by default. Let's further look at these materials and say, what are these objects made up of? What metals are they using? For grounding systems, those are generally always copper, but we can also throw in steel rebar and concrete, also galvanized fencing, and some grounding systems are made up of galvanized steel or zinc, or possibly could also be copper. The challenge is, with all of these materials in a common electrolyte in the soil, and all bonded together, there is a galvanic corrosion cell created, or when we bring in an active cathodic protection system, we wouldn't want to inadvertently bond it to all this collection of metals. Let's go back now to our equipment grounding conductor, now that we've laid out the whole station and some of its complexity, and say we have to decouple this equipment grounding conductor so that the ground of the motor-operated valve does not short out the CP of that section of pipe. Also note that there's another equipment ground that we ran to the main building, say for a gas metering set. Now, why are we allowed to even do equipment decoupling? The reason that equipment decoupling can be allowed in specific cases is because first we must go back to the electrical grounding requirements that are nationally, say in the US or in Canada, addressed by the National Electric Code or the Canadian Electrical Code. So each will have a section on grounding, and the purpose again of the grounding requirements is so that fault current can be handled, the conductors are sized appropriately for that current, that it is low impedance and therefore allows heavy current flow and a breaker to detect that fault and then clear the fault. Decoupling is allowed if a listed, meaning a certified device, is installed according to two code sections, one in the US and another in Canada, that make explicit allowance for this. As long as the device has been third-party certified as having adequate fault current ampacity, is fail-safe, and meets these code sections, it may be used. You'll know that. You'll see a certification mark, such as on the screen here for UL. There can be other third-party services and their marks also that would indicate that the use of that device is allowed for meeting cathodic protection requirements and also safety grounding. So now where will we put this decoupler to address equipment grounding conductors? We could try to do the same thing that we addressed earlier with the signal cables. What if we used a single decoupler to decouple both grounds, one to the motor-operated valve, one to the building? Well, that means that both grounds are going to land on one of these decoupler terminals and put them together in common. Can we do that? Well, no, we really can't do that. The reason again here is that while the motor-operated valve and its ground are on a cathodic protection system, the equipment in the building is on a non-cathodically protected system and is tied already to ground. We cannot bond those two together, or else the galvanic system, CP system number 2, is going to end up being bonded by default, ironically, at the point of a decoupler, to the system, the grounding system of the station. So that's an unacceptable choice. It also is that we don't need to address the ground that runs out to the equipment in the building. There's no CP involved. What we can do as a final solution is to place a single decoupler, for our story here, just in series in the grounding conductor for the motor-operated valve, and we also address metallic conduit if that's present. And we have now decoupled the cathodic protection that would otherwise be affected by this grounding conductor, and yet we still meet grounding codes and have safety grounding. You would use the same kind of analysis to consider if multiple pieces of equipment can use a common decoupler or not. The way to think about it is, do these grounding conductors or these pieces of equipment come from, or are they located on, a common cathodic protection system, or are they separate cathodic protection systems? If they are separate CP systems, you would use separate decouplers so that each system is properly decoupled and one system is not inadvertently bonded to another. Now, I've shown the decoupler here graphically just out in the middle of the grounding conductor, but one wouldn't really do this. You would either locate it at the disconnect panel on the building, or you would locate it out at the motor-operated valve. Is there any advantage one way or the other? On the face of it, you'd say no. In both cases, the decoupler is in series in the grounding conductor properly, and it would be a true statement. But consider also that if conduit is in contact with the pipeline, it is part of the cathodic protection system up to the point of decoupling. The closer you locate a decoupler out near the pipeline, the less of that conduit run is part of the CP system, and therefore it's harder for an electrician to go and bypass it later in the future if they were to hang a clamp off of the conduit or do something with that conduit. Therefore, generally, a more foolproof system is where the decoupling points are closer towards the pipeline. Now let's look at a couple of bonds that might exist out near the fence and near the gradient control mat. Can we install hardwired bonds like we see here? What effect will that have on cathodic protection, if any, and do we need decouplers or solid bonds okay? Well, in this particular case, the fence, which is galvanized steel, can be bonded to a galvanized steel gradient control mat or a zinc grounding mat. That would be compatible with no decouplers needed. But in the case of the cross-country pipeline, we've labeled it CP1, that's an impressed current system that we would not want to bond directly to a grounding mat system, even if it were zinc or galvanized steel. It's going to create an extra demand on the impressed current system, and it might affect cathodic protection potentials. So we would use a decoupler in series in that bond. Here's an image of a block valve site that's been built and issues about what can be directly bonded and what needs to be decoupled. In this case, of course, our pipeline has cathodic protection, and therefore on our left-hand picture, you'll see a decoupler, the black cylindrical object, connected to between the pipeline and the gradient control mat, and that's the silver-looking grid all around the pipe. So the decoupler completes the safety connection between the mat and the pipe so that for a user contacting the pipe and standing over the mat, the voltage would be very low. But for cathodic protection, those two materials look like they're not bonded to each other. As we look at pictures on the right, you'll see that the mat in this story has extended beyond the fence. Why would they do that? The mat extends beyond the fence because then as a user even approaches the gate, approaches the fence, they're already standing over the mat and therefore they can receive protection. In the case of galvanized steel fencing and posts and this galvanized steel matting system, those could be bonded together directly without effect on CP. Not shown in this image is when the entire facility is installed, the gravel that you see in our pile over on the right is going to be installed over the top of this mat. Gravel, if it's a high resistivity fill, adds an extra insulation layer to even further insulate the user from any effect or defect in a gradient control mat system and isolate, limiting how much current can flow through their body. There's one last area we need to talk about that can be a bond to grounding systems, and that is a connection to the power company. Now, in our station here that we've been designing all along, we actually, if we've done this right, have not created any inadvertent contacts of the pipeline with cathodic protection to the system or the station grounding system. So we really would not have to address the connection to the utility if we've done all the other things we've talked about. However, let's make this station more complicated. Let's say that this station actually was a compressor station or a large pump facility. It could be that there's much more equipment and piping than I've shown right here, and there's many points of possible contact of the pipeline to the grounding system where the CP could be shorted out. Those sites can be so complex that you can't even sort out all of those bonds, because if you missed even one, it's like you had done nothing at all. Then you might be able to see how separation from the power company becomes important. Because by default, power company grounding systems connect to user grounding systems for safety. And it's that tie that we have to address. Here's a picture that's been blown up of our same installation, showing that we have incoming power from a utility, and I'm only showing the neutral here. And that comes to a transformer. It doesn't matter whether it's a pole mount or pad mount transformer, single phase or three phase. It will come in and it will get bonded to the customer's neutral. They bond at the tank. Further, the customer's neutral is tied to the disconnect panel in the station, and that ties into the grounding system. So that's how the customer's neutral gets tied to ground. On the utility side, their neutral is also grounded every several poles, and they're bonded not just to their own grounding system, but tied also to every other customer that they serve. So your station CP could be bonded to a massive extended grounding system. There are 2 points of possible decoupling and isolation for cathodic protection when it comes to your incoming power from the power company. And there's going to be many more details than we could ever talk about in this presentation, so I'm only going to just introduce the subject. At points 1 and 2, those are possible points of isolation and decoupling. One of those could be done by the user, and that's point number 1, because it is done on your side of the meter. There's another solution that can be done by the power company at the transformer because they own that part of the system. And if appropriately installed, again, a subject much too broad for covering here, you can have acceptable CP isolation and yet meet all of the safety bonding needs of the tie between those two systems. A couple of last thoughts. As I just mentioned, you have to balance complexity and the need for CP isolation as you consider overvoltage protection. Some very complex sites are not well suited to having every single point of bond between the pipeline and its CP to a grounding system just because there's too many of them. And that's where you'd look at separation instead from the utility. There's another thought, and that is sometimes your facility has a neighbor right across the fence, perhaps another pipeline system that you buy or sell material from. Their cathodic protection system, their bonding, and their grounding may affect yours, whether or not you have a CP system. It could be that they cause interference with you, and that's another case where even if you didn't have anything cathodically protected in your station, you may need to separate your service from the other customer. Finally, some of these solutions are done in a classified hazardous area. So Elsewhere in your company, someone may have classified this site to have different risks, such as a Div 1 site versus Div 2 versus ordinary location, and appropriate products have to be used and appropriate methods have to be used in each of those areas. So the least restrictive would be a non-certified, non-classified site, followed by a Div 2, and finally the highest classification would be Div 1. And there's also a common zone system, so you may hear reference to Zone 1 or Zone 2, and that's effectively the same thing. There's just different standards out there. The issues are that an appropriate product must be rated and chosen and installed to match the classification of that site. So if you need to protect an insulated joint, it might be classified as a Div 2 site. You would use a Div 2 rated product, and that's a certified product for that installation. What you would not want to do is have a classified Div 1 site, but not want to purchase a Div 1 product and instead say, I'll just buy a Div 2 device and I'll move it outside of the Div 1 area and connect it all with longer leads. That is not a good choice, and the reason is you've introduced excessive conductor length, which adds inductance, which then has problems during lightning conditions due to fast rising waveforms. It's back to that issue of inductance of the leads. So there's an entire topic also built around hazardous locations, product selection, and use, but this is just an introduction to say don't forget about that topic. In short, proper overvoltage protection can be accomplished at the same time as optimizing cathodic protection so that both can play nice and stations are built correctly. If you have questions about any of these matters, feel free to contact us at the email that you see here. We're glad to answer your questions.